Good morning, everyone. It's my pleasure to introduce our speaker today, Dr. Thayne Currie of the University of Texas, San Antonio. Thayne will be talking to us about very exciting results that he's recently obtained and will be obtained in the future by using ground-based extreme adaptive optics imaging of nearby stars and looking for their disks and protoplanets. Thayne did his undergraduate work at the University of Wichita, right? Wichita State University in physics, then went to UCLA to get a master's and a PhD in astronomy. He did a postdoc at the University of Toronto. Then he joined the Subaru project, which is based on Mauna Kea. You can see, I think that's a profile of Subaru there showing on his slide. And he's been working there for many years. In fact, most of the results I think you'll hear today are from the Subaru telescope. And along the way, he's also been working with a group at NASA Ames, which is a group there that's also involved in doing high contrast imaging for future space telescopes as well as ground-based telescopes. And just recently, he's become a professor at the University of Texas, San Antonio. So we need to congratulate him on that treasured position. And with that, I'll hand it over to you, Thayne, and take it away, please.
All right. Well, thanks very much, Alan. It's nice to be back. I guess in air quotes a bit at Carnegie. I think the last time I was here was many years ago when you still had the tradition of having food together around noon. So I'll miss that, but it's nice to be back, and I see some familiar names here. I'm going to be talking today about work I've been doing in the past couple of years, focusing on studying planet formation with the Subaru Coronagraphic Extreme Adaptive Optics project. So focusing on imaging disks around young stars that show evidence for planet formation, and as I'll show during the course of this talk, evidence for protoplanets themselves in at least one of these systems. Okay, so to motivate the talk, we want to be able to understand planet formation, how we go from the initial starting point of planet formation to the finished product. So nearly all stars appear to be born with the building blocks of planets, gas and dust surrounding these stars. These are protoplanetary disks, typically on the order of about 1% or a few percent the mass of the star. And they appear to show up around a very large fraction of young stars, possibly all young stars are born with with protoplanetary disks capable of building at least some planet mass objects. We've also identified 5,000 planets around nearby stars, including about 20 that have been directly imaged. Now, these form this sort of extremes of planet formation. You see these on the rightmost series of panels. Planets that are in excess of several times the mass of Jupiter, orbiting at semi-major axes in excess of about 15 a year or so. Now, these planets are stressed in terms of being able to be formed by standard planet formation models, including core accretion. So they may identify the extremes of what the sort of standard model for planet formation can produce, or they may identify entirely different mechanisms for forming massive planets, namely disk instability. So to be able to understand this transition from the initial planet forming stage to the finished product, we need to be able to resolve disks that seem to show evidence for incorporating the raw material planet formation into the finished product, namely transitional or transition disks. Basically, these disks show evidence for active planet formation. The sort of canonical picture is that these disks appear to have regions that are cleared in small dust grains on solar system scales. They also may show other features such as asymmetries or spiral density waves. And there are many examples of these disks that have been imaged with ground-based telescopes or in space. This is one sort of canonical example, PDS 70, which shows a clear gap in near-infrared polarized light. It shows a clear gap in the submillimeter. And then in this particular system, we see evidence for a protoplanet that's been directly imaged. So we want to be able to study these systems. And there's a wide variety of transitional disk morphologies that we've been able to identify in infrared light. And this is showing just a gallery of some of these. Again, you see some systems that show evidence for spiral density waves. You see some that show evidence for just cleared gaps. There's a wide range of morphologies for transition disks that may map onto a wide range of planet formation conditions in these disks. And we want to be able to directly image not just the disks in these types of systems, but the planets themselves. So that's what we try to do with the Subaru Chronographic Extreme Adaptive Optics project. So I'll talk a little bit about the design and performance for this system. I'll talk a little bit about the instruments for studying planet formation, how they are specifically well tuned to be able to attack this problem. And I'll focus on two major examples for studying planet formation with SCExAO. First is a system called LkCa, and the second is a system called AB Aurigae. I'll also include a very brief discussion of an additional system. It's not technically a system that's actively forming a planet, but this is a newly formed planetary system. If you don't care at all about planet formation and somehow stumbled onto this talk, it is still worth staying on to this particular aspect of the talk. It has a sort of a broader lesson, I think, that may be applicable to your own research. I'll talk a little bit finally about some upcoming studies of planet formation with SCExAO. Specifically, these will be driven by upgrades to the system. I'll talk about the new science capabilities that are enabled by these upgrades. So first, I'll discuss what the instrument we are using to be able to study planet formation, the Subaru Chronographic Extreme Adaptive Optics Project, or SCExAO. So this is an extreme system for the Subaru telescope. Olivier Guillaume is the PI. It uses advanced wavefront sensing and correction capabilities. So it uses a pyramid wavefront sensor to be able to sense the wavefront, and uses a 2000 actuator Boston Micro Machines deformable mirror to be able to correct for it. It's able to apply these corrections rapidly and with high precision. So in excess of 1,000 modes, and it can run up to 3.5 kilohertz speeds. We typically operate at about 2 kilohertz or so. Is able to achieve very sharp images of stars. So quantitatively, we can get straw ratios in excess of about 90% in H-band. And it's coupled with a suite of instruments to be able to record scientific data, including the Currie integral field spectrograph, which is kind of our workhorse image. Now, the plots on the bottom panel, the bottom sets of plots show the AO capabilities, the sharpness that we're able to achieve for SCExAO. So we're able to achieve extreme AO corrections on very faint stars in the optical. We're able to get diffraction limited images in the optical, and we're able to get very nice images of known planetary systems, such as the HR8799 planetary system. So in terms of a schematic, this is how it works. SCExAO actually is a second order correction for Subaru. So it sits behind the facility adaptive optics system, which is a 188 actuator deformable mirror curvature wavefront sensor. It's able to get a very modest correction of atmospheric blurring. So in excess, on the order of about 30 or 40% straw in near-infrared wavelengths. Now, this partially corrected starlight is then sent to the SCExAO loop. The pyramid wavefront sensor senses the residual atmospheric blurring. It corrects for it with this deformable mirror. The sharpened starlight is then blocked by a chronograph. And then in the infrared, this sharpened starlight, which is then with the halo that is suppressed, is then sent to Currie. In the optical, this light then be sent to a suite of different instruments, vampires being the chief instrument that we'll be focusing on for this talk. And again, quantitatively, we're able to do very well on sky. So about 90% straw, maybe in excess of that for very bright stars, and extreme AO corrections down to even about magnitude 7 or 8 or 9 in this particular case, and then diffraction limit images in the optical. So what do we do with these very sharp images of stars and extreme AO capability? Well, the near infrared, what we were able to do when we couple SCExAO to Currie, we're able to get spectra of planets. So this is showing a simple example. This is the Kappa Andromeda B planet, where you get a very nice detection, about a signal noise of 210 in this particular image. And we're able to get a spectrum that shows evidence for water and carbon monoxide in the atmosphere of this planet. Now, for protoplanets, what this means is that we're able to get a good spectral energy distribution of any candidate protoplanet that we detect, going from about 1.1 to 2.4 microns. And this very long wavelength baseline allows us then to be able to study in detail the spectral energy distribution of our candidate protoplanet, possibly compare it to different models for protoplanets or models for scattered starlight, which would be the other possibility for a signature that we might identify as a protoplanet. And we have two other capabilities for our program that allow us to be able to interpret young planet-forming disks in a little bit more detail and better distinguish between protoplanets and disk features. So the first is we have H-alpha imaging capability in the optical with the Vampires instrument. And this operates, H-alpha is just a dual band imager. We have two cameras that operate simultaneously for this. It's sort of analogous to what is available on the MAG-AO system with their H-alpha differential imaging mode. And in this particular case for MAG-AO, we see this demonstration of a nice detection of a protoplanet, PDF70b. We want to do the same thing with SCExAO. Additionally, we can operate Keras not just simply in total intensity mode, where we just get the light from 1.1 to 2.4 microns, but we can do polarimetry in every single one of the wavelength channels in which we would normally study a planet or a disk in total intensity. So this integral field polarimetry capability allows us to better distinguish between planet emission and disk emission, because we're getting a detection at 22 separate spectral channels at a time to complement our detections in total intensity at those same 22 spectral channels. So we can be able to identify differences in the brightness, spectra, and the morphology of any features we might identify as a protoplanet in both total and polarized intensity. So let's move on to sort of our case studies for studying planet formation with SCExAO. So the first is LkCa 15. So this is a lab long been known as a laboratory for studying planet formation. It is a key target for searching for protoplanets. Now, we've known about LkCa 15 as an important system since the 90s or in the 2000s. And we can identify LkCa 15 as a key system just by looking at its spectral energy distribution. So the plot on the left shows a spectral energy distribution fit from Espelade et al. 2007. We see the data in the optical as empty circles, and as we get in infrared and then the mid-infrared, we see evidence for not just simply detection of the photosphere of the star, but also its disk. But unlike a lot of other disks in Taurus, we see evidence for a depression or a missing emission in the mid-infrared wavelengths. And this could be mapped onto what we expect for a gap in the disk or a depletion of sub-micron sized dust grains on solar system scales. Now, if we look at scatter light or in the sub-millimeter, we can actually image this inner gap or a hole in this system. So the plot on the right shows evidence for a gap in the disk from Andrews et al. And where we see a cleared cavity on the order of about a few tenths of an arc second in semi-major axis, roughly on solar system scales in this system. So we might expect that there might be at least one Jovian mass planet in this particular system that is clearing the dust grains in this disk. So in 2012, we had actually the first potential evidence for a protoplanet in this particular system in LkCa 15. You know, this sort of LkCa 15b, which had this sort of very strange morphology. If you look at it in a little bit more detail on the image on the upper right, where it appears to be this sort of concentrated emission at K-band, so about 2.1 microns, and this sort of arc of emission at L-band that seems to be flanking the central emission source. But then follow-up data obtained with the LBT telescope seem to refine this picture, where we instead see three separate point sources, or point-like sources, LkCa 15b, C, and a potential D companion. Now, sparse aperture masking, which is the technique used to be able to find protoplanets in this system, is very powerful, but it also can be very dangerous because it can be very difficult to distinguish between a point source and an extended source. And you can fit the same signal, same closer phase signal with both morphologies. So instead of using sparse aperture masking to sort of infer what the structure, what the signal is, we actually try to directly image the inner regions of LkCa 15 themselves with SCExAO, and we also have complementary data from the Keck telescope. So what we see then is instead of 3 point sources, we see a continuous arc of emission tracing the inner edge of a bright inner disk that had been previously unidentified in some millimeter and had not been well identified in the near infrared. And LkCa 15 B, C, and D's positions appear to trace the edge of this inner disk. The disk at K band and L band, where LkCa 15 B, C, and D had been purportedly identified, is roughly equal in brightness to the total flux reported for these candidate protoplanets at the same wavelengths. So we think that we're getting the same emission from what had been identified as these protoplanets. And then we use forward modeling to be able to test whether we could have identified planets fainter than LkCa 15 B, C, and D at these same separations. And we, in fact, showed that we could. So it appears that this emission might be the same thing that had been previously identified as 3 candidate protoplanets. To test this in a little bit more detail, we had used advanced forward modeling. So we took our data and we forward modeled the signatures of 3 protoplanets in the system and see what they would look like if they actually were in our data. And so they would actually appear as 3 separated point sources in our SCExAO data. The Keck data, which is complementary to what we obtained with SCExAO, shows additional evidence that what we're actually seeing with these candidate protoplanets is instead a bright scatterlight, the bright forward scattering edge of an inner disk. So we take data taken in 2009 and we forward model the positions of LkCa 15 B, C, and D. We see a continuous arc. It's very difficult to distinguish between an inner disk and protoplanets because point sources would appear to be exactly like this inner disk. But over the course of about 8 years in this particular system, these protoplanets would change in position angle over time because they're orbiting. And so this arc would appear to rotate as we go to data taken in 2017. But we see a difference between the scatterlight appearance of this inner disk and what we would expect to see for LkCa 15 B, C, and D if they were actually protoplanets instead of misidentified disk signatures. So what we conclude basically is that we're seeing an inner disk instead of protoplanets. And then we actually try to understand this from first principles. We have our data with SCExAO and Keck. We forward modeled a scatterlight disk image using the MC-Max 3D, and we're able to get a pretty good fit to the data. So the residuals are much fainter than any purported protoplanets in this system. So we don't see any residual point sources at LkCa 15 B, C, and D's position. We weren't actually able to discuss a separate evidence for a protoplanet in the system, namely a claim detection in optical in H alpha. But that's we have skepticism about that for other reasons. But basically, what we're able to show the power of SCExAO to be able to study a young planet-forming system in detail and better distinguish between bona fide protoplanets and disk features. So that one system was a little bit of a downer for us. We would like to be able to directly image protoplanets. Fortunately, we also have tried to observe other systems, and we have some different results with these. In particular, the system called AB Aurigae. So like LkCa 15, AB Aurigae has long been considered a planet formation laboratory. Its disk is very highly structured. It's a beautiful system. It's been resolved since 1999 from data taken with the Hubble Space Telescope. Now, data taken from the ground with the predecessors to SCExAO showed even more structure. So data taken in the early 2000s identified a series of spiral arms around AB Aurigae, which could potentially be mapped to planet-induced structures, that there may be planets that may be responsible for launching these arms. Now, if we look in polarized light a little bit closer, we see additional structure in the system. And this is shown in the second to the left panel, where we see multiple components to the AB Aurigae disk The innermost region sort of looks like this weird sort of like baby Godzilla, potentially additional spiral arm. And so there's a lot going on in this system. Now, if we look at the submillimeter, we see additional evidence for something special going on in the system, additional evidence for spiral arms and cleared regions. So if we look at gas, we see 2 spiral arms in this system. Now, if we think that these are actually spiral arms launched by an embedded protoplanet, the authors of the paper reporting these data, Thayne et al., identified potential locations for where these protoplanets might be. Now, these are denoted in triangles. So both of these positions are roughly due south of the star at separations about 0.2 arc seconds and about 0.6 arc seconds. And then finally, if we look at dust, we see an additional cleared cavity. So we see this region outside of about 100 AU or 100 to 10 AU or so that appears to be devoid of pebble-sized dust. So we have all these different lines of evidence that suggest to us that AB Aurigae is a system worth looking into in more detail. Also, apparently Hollywood agrees. So as we had a paper that was reporting results on AB Aurigae from SCExAO, as that paper was under review, and actually as it was nearing final acceptance, this paper showed up. Sorry, this movie showed up. Don't Look Up, and if you actually paused about the 2-minute mark, where the 2 astronomers were observing at Subaru with the lights on, of course. But if you pause about the 2-minute mark, you can actually see one of the early images for AB Aurigae on the screen. So that was very interesting when we were still worried about being scooped for our result. So, and again, just to follow up, AB Aurigae has indirect evidence for planet formation, spiral arms, a clear dust cavity, spiral arms in the submillimeter and CO gas. This is something we want to look into in a lot more detail. And so we did, and we get this detection of a sort of bright blobby structure almost due south of the star, AB Aurigae B, as we call it. This is a point-like feature located inside the ALMA dust screen. So we show a composite of the Arcturus data in blue, ALMA in red. It lies inside the ring, roughly where you expect a protoplanet to be if it's clearing out the ring. It is also dead on consistent with the predicted location for an embedded protoplanet from the CO gas data. Now, the image on the right shows the same data, shows data at a later epoch in 2020, scaled by the cell-centric distance and with a little bit more processing applied to the system using something that's called a polarimetry constrained reference differential imaging. Basically, what this means is you get a truer, higher fidelity image of what this system actually looks like, and we still see this really bright blobby-like structure that appears to be sitting on one of the spiral arms in this in the system, almost due south of the star. Again, consistent with the predicted location for an embedded protoplanet around this particular star. So we also took data with the Hubble Space Telescope because we wanted to be sure that we were detecting a real structure and we're not detecting a structure that appears to be point-like due to processing. So we obtained new data with the Hubble Space Telescope with STIS in 2021, and we see a very easy detection of AB Aurigae B. We also looked in the archive and found an archival detection of this feature in NICMOS data from 2007. Now, the interesting thing about these two data sets together is that they show evidence both of detection with two different instruments with HST, but also evidence that this structure appears to be moving. And we show that by comparing the sort of like a direct vertical line, which is the position angle of 180 degrees in the system. Compare that to the position of AB Aurigae B in both these images. So in the NICMOS data, that is the AB Aurigae B appears to lie to the left, and the STIS data appears to lie to the right. Okay, so this would be consistent with a difference in the position of this object consistent with orbital motion. In fact, if you look at data taken over several epochs, even with Currie, you can start to tease out evidence for orbital motion. So this is data just from 2016 to 2020, 2021, where you see this thing move ever so slightly. Now this is only over a couple of years time scale. You can see this movement a little bit more clearly if you look at data with HST taken over 14 years time scale. So that's what we see on the image on the right. If we try to model the astrometry, we get the following results. So we see the position angle change from about 278 degrees to about 184. So 178 degrees to about 184 degrees. The inclination for the system is a little bit inclined with respect to the disk. Its semi-major axis is probably around 90 AU or so. It's moderately eccentric. This would be roughly what we might expect for an object that is nested within the disk, or at least we're just very slightly inclined. Now, the other test we want to make with AB Aurigae B is try to understand what its emission looks like in different diagnostics. So if this is a disk feature, we expect it to be detectable in total intensity and in polarized intensity. And we're not sure we would expect to detect it in H alpha. What we see with AB Aurigae B instead is we have a clear detection in total intensity. This would be the type of light that would be, the type of observation that would well probe thermal emission from a protoplanet atmosphere is very clearly detected. In polarized light, which tends to probe small dust grains, but not the atmospheres of planets very well, we do not see a clear detection, so it does not light up very well. But we also see a detection in H alpha, which appears to be a diagnostic of accretion in many other systems. So we have a detection in total intensity, which is consistent with detection from the atmosphere, a non-detection in polarized intensity, and a detection in H alpha. So these three lines of evidence combined together give us a stronger indication that we might actually be seeing a protoplanet instead of a misidentified disk feature. Now, if we look at the spectrum in a little bit more detail, we see further evidence that AB Aurigae B's spectrum is inconsistent with what we expect for pure scattered starlight. We're able to reproduce the spectrum by roughly a 2000 Kelvin source, coupled with about a 10,000 Kelvin magnetospheric accretion source that would be responsible for its emission in the optical. The overall luminosity of the system is roughly what we expect for about a 9 to 12 Jupiter mass object. All right, so if we're seeing direct light from a protoplanet, or at least light that is reprocessed, light from a protoplanet that is then reprocessed, this is roughly what we would expect for a super jovian planet. The last piece of information, though, that is a bit complicated, though, is that how do we explain the appearance? AB Aurigae B is not a point source; it's actually spatially extended. And at the distance of the system, that would correspond to an object that would be several AUs in size, which is not what we expect for a recently formed or actively forming planet. Those should be much smaller. So we're able to explain this particular feature using radiative transfer modeling. Basically, if we're seeing an embedded protoplanet in a marginally optically thin disk, that protoplanet's light is intercepted by the disk and reprocessed, and is made to appear spatially extended. And we can actually reproduce what we see by embedding AB Aurigae B in a disk where the local optical depth is about unity or so. And we also use the same model to be able to explain its non-detection in polarized light. So we think we have a sort of good overview picture of what we're seeing, both as a function of wavelength, as a function of diagnostic, what we're seeing in terms of the morphology of this object. If we combine all these lines of evidence together, we favor evidence for an embedded protoplanet at wide separation whose spatially extended appearance is due to the fact that it is an embedded object. It's still there. So we have new detections for this object taken subsequent to our paper. These two data sets were taken in 2021, and then about 6 weeks ago, The detection is still there. The important thing to learn from these sets of images, though, is that the morphology of the disk appears to be different depending on exactly how we process the data. So you have to be extremely careful with structured protoplanetary disks in interpreting them, because you may accidentally tear up or distort the signals of these disks in complex ways if you're not very careful. These are just images, quick look images. It will take some time to be able to extract what the true images of the disks are in this image, and what the true brightness of our claimed protoplanet is in these images. So what's the broad significance of this detection? Well, what we think is that this is, if our interpretation is correct, this is a super jovian embedded protoplanet at a wide separation on the order of about 90 AU from the star. This is far larger of a separation than we think is possible to be able to explain this object by standard models for jovian planet formation, namely core accretion. So we have to be able to invoke an alternate model. So the alternate model that Carnegie's and Alan Boss has championed is planet formation by disk instability or gravitational instability, as has been otherwise known. The basic idea being that the disk is initially so massive that in the outer cool regions pieces of it are able to collapse under their own self-gravity and form fragments, and these fragments then become massive protoplanets. For some reason, this animation is not playing right now when I'm showing this slide. But if it were playing, you would see a series of clumps form in simulation on the left, and these system you would have at least one, possibly more clump-like protoplanets form in a system with spiral density waves. This roughly matches what we think we see with the AB Aurigae system. In fact, some of the simulations of planet formation by disk instability by Allen and by other authors have an uncanny similarity in appearance to our data. So we have other planet forming disk results from SCExAO. We haven't found any other protoplanets yet in these particular systems, but we do find a lot of very striking images, and these are in various stages of completion. So we have one system that's published, this HD 34700. This is actually this weird sort of composite system of a cleared ring with a set of spiral arms that appear to emanate from the ring. We also have imaged MWC 758, which is another system with claimed protoplanets. We don't see any protoplanets in this system, but we can keep looking. Perhaps deeper data will identify them. And we also have other systems that we're following up. In particular, this one, which is unnamed, which appears to be this sort of concentric ring system identified in total intensity, but in polarized intensity, we only see one of the rings light up. So there's a lot of data that is currently in the pipeline in various stages of analysis. Hopefully, this will be published soon. So I want to have one segue to this discussion, the complementary programs. And the reason why I bring this up will become very clear in a second. So a lot of people, or at least some at Carnegie, I think Alan and Dr. Weidenberger, have also been interested in planet detection by astrometry. And so a parallel program that we conduct often on the same nights in which we try to image planet forming disks is a survey to detect planets simultaneously with astrometry and direct imaging. Basically, we use the Hipparcos Gaia catalog of accelerations. So this is a catalog of stars that show statistically significant accelerations from combining Hipparcos and Gaia data. We target stars with statistically significant accelerations for direct imaging. And we've identified a number of substellar companions, and our first planets from this survey. This is HIP 9977b. This is a directly imaged planet around an accelerating A-type dusty star. So this star also has a young Kuiper belt. We have a very nice high signal noise spectrum. So a spectrum that shows evidence for water, carbon monoxide, perhaps also methane, is best fit by an object right at the LT transition. So this probes the transition from cloudy to clear atmospheres in substellar objects. And this is a really interesting system because if we look at its spectrum, it appears to be intermediate between an old field brown dwarf and a young ultra cloudy planet like the HR 8799 planets. And it also may be detectable in future NASA space missions with the Roman Space Telescope in the optical. So we can kind of think of it in terms of probing evolution or probing planet formation. This is a system that allows us to sort of see the change in the atmospheres or the atmospheric evolution of young planet mass objects. Now, because we have a detection of this planet in direct imaging and a detection in astrometry, we can get a lot of information about the orbits and the mass of this object. So if we combine the relative astrometry of the companion with the absolute astrometry of the star, we can simultaneously model these two separate data sets to be able to constrain the semi-major axis, eccentricity, inclination of the planet, along with getting a direct dynamical mass measurement. And the corner plot shows the consequence of our dynamical modeling. We're able to get a very precise measurement for the mass, a precise measurement for the semi-major axis. This eccentricity is fairly low, and it's on a slightly inclined orbit with respect to our line of sight. If you think of this in terms of solar system analogs, this planet is receiving roughly as much light as Jupiter receives from the sun. And the mass ratio of this planet appears to be roughly comparable to the mass ratio for a lot of planets detected by radial velocity or other indirect techniques, as well as some of the first directly imaged planets like the HR 8799 planets. Now, here's the part that's relevant for those of you who are not interested in exoplanets at all. I'll call this the saga of post-refereeing for this object. So this paper passed external peer review by July 5th. It probably actually passed it before then, where all three referees recommended acceptance. And so in science, this means the next stage is you go to a handling editor for edit requests prior to official acceptance and publication. So on July 5th, we were told there were several papers ahead of yours in the queue. It will likely take weeks, not days, for this process to complete. On August 25th, we were told there are still numerous papers ahead of yours. September, I'm afraid your paper is not close to the front of the queue yet. It's likely to be several weeks or days. November, I cannot make an estimate. Realistically, it's unlikely to be before Christmas. So basically, the reason why this paper is now in archive is because I got tired of waiting, not because the paper has been officially published yet. Hopefully, this will happen soon. But for those of you with different programs, like maybe some JWST programs, like with the Transiting Planet ERS, this is a data point that allows you to consider where you might want to submit your paper, especially if in the future there are no proprietary periods for your program. Just an aside. Okay, so where do we go in the future with this program? So in the future, we're going to be able to greatly increase the power with which SCExAO can study planet formation, in particular, studying planet formation around low mass stars. This will be driven by technological updates with SCExAO itself. So the first major update we're doing is we're replacing the wavefront sensing capabilities for SCExAO. We've been doing this in the optical. We'll now be able to do this in the near infrared. Now, what this means is that we'll be able to study planet formation around very young low mass stars that would be inaccessible with adaptive optics before. So there are a lot of stars with that show evidence for active planet formation that are like 13th, 14th, 15th magnitude in the optical. You can't target these very well with an adaptive optics system, but they're on the order of about 10th or 9th or 8th magnitude in the near infrared. So if we focus our wavefront sensing capabilities in the near infrared instead of the optical, we now can get sharp images of these stars. Additionally, we're replacing the front end for our facility adaptive optics system. Instead of having only 188 actuators, we'll now replace it with a DM with 3,200 actuators. Effectively, what this means is that we will get an extremio correction even before we get to SCExAO. And SCExAO will then further sharpen the images of these stars. The first flight for this new upgraded system is in a few months. It was supposed to be in November, a few days ago, but we had some delays with delivery of our DM. So look for this to start to happen maybe around February or so. And what this means is we're able to get extremio corrections for optically faint stars. This shows roughly our magnitude limit as a function of wavefront sensing passband. So even if we focus only in wideband, so blue words of all the Currie wavelength channels, and run at full speed, so run about 2 kilohertz, we're still able to get a true extremio correction for stars that are 9th magnitude in wideband. Now, a lot these describe a lot of stars that are M stars in, for example, the Taurus Aurigae star forming region. So we're opening up a new phase space for getting extremio corrections around stars with planet-forming disks. And then if we sort of tune this a little bit, so if we sacrifice J-band or run slower, we can start even fainter stars. And these would be comparable to the brightnesses we'd expect for mid-M stars in some of the nearest star-forming regions. And if we try to quantify our sensitivity, what this means is we can finally start to be able to detect young, recently formed Jupiter mass planets on solar system scales around some of the most abundant types of stars in the galaxy, so M stars. And there's a very good sample of these stars that do show evidence for clearings or gaps on solar system scales. The plot on the right depicts this. A lot of these are completely unobservable with previous programs, or at least or perhaps poorly observable. So this new program, SCExAO Direct Imaging Survey of Planet-Forming Disks, will be sensitive to Jupiter mass planets in the gaps of planet-forming disks around many low-mass stars to complement our focus right now on trying to image planets on stars that are optically bright. So that's basically my talk. The only other thing I wanted to add at the end is that this work could not have been done without the support and dedication of the Subaru staff, technicians, IT engineers, day crew, office workers, who've done amazing work in the last couple of years as things in Hawaii have had a bit of a wild ride for a wide variety of reasons. The most recent one now appears to be another lava flow. So they've done extremely well making the observatory work flawlessly and also been giving back to the community at the same time. So that's my talk. I'll take any questions you may have.
Okay, thank you very much. Thayne, a very thorough talk and very nicely explained for those in the audience who are not experts in extreme adaptive optics. So, and it's some very exciting results, especially this new stuff about the HIPAA 99770. And it's an unfortunate choice of science is the journal to publish it. That's quite a remarkable story about the hindrances you encountered in getting the paper actually finally published. I mean, that's just absolutely unthinkable what's going on in science, but I'll be curious to see what the rest of the story is and when it finally appears. So let's see, do we have some hands up for questions? None yet, but please do raise your hand. I have a starter question for you, which is for the AB Aurigae system. As you point out, the blob that's off 78 AU or so away is kind of seems to be rather large and extended. You're not quite sure exactly what's going on there. But I presume that target would be a great one for NIRCam on JWST to do. Do you know, are you proposing to do it or someone else has done it? I mean, your paper was published already this year, so lots of people know there's an interesting target there. How good of a job would JWST do on that target?
Sure. So I'll preface that by saying I actually did submit a proposal for AB Aurigae for cycle 1, and for whatever reasons, the TAC wasn't happy. Hopefully they'll be happier this time. So there are pros and cons to be able to imaging this system with NIRCam. So the con basically being is that the PSF or JWST NIRCam is very, very complex and the resolution is poor. than the resolution you would get with Subaru. And so if you combine these two things together with the fact that the disk is highly structured, if you sort of like convolve that entire system with the instrumental PSF, there are some worries that it could be tough to distinguish between the planet and the disk at wavelengths where the disk gets to be rather bright. So long words about K-band. So we've tried to detect AB Aurigae B in the thermal infrared at L prime and have failed from the ground. And this has been due to the fact that our data were just not that particularly good because the seeing was poor on the days we took the nights we took the data, and then also just because the disk is really bright compared to the star there. So that's one complicating factor that makes the case for NIRCam a little bit more challenging. So any proposal that tries to seek to detect AB Aurigae B with NIRCam needs to clear that hurdle first, I think. And so that's going to be something I'm going to be focusing on. On the plus side, you're in space. You don't need to do any complex PSF subtraction. This is a bright object. So it makes interpreting the system far easier. You don't have to do complex forward modeling that you have to do on the ground-based telescope. So that's one major advantage. I think the other major advantage is that because you're above the atmosphere, you can operate at wavelengths that are inaccessible from the ground. So slightly longer, long words of 2 microns. You know, the thermal background is just not there at 3 to 4 microns compared to the ground. So those can be particular advantages, I think. So long as you can convince yourself they can really distinguish between a concentrated point source and the disk, I think the case for NIRCam is very strong.
Okay, as another question along that same line, you mentioned some of the upgrades that are being planned for Subaru Extreme AO. Will any of them qualitatively or quantitatively improve the imaging for AB Aurigae? Can you give sort of an estimate of how much better you'll be able to constrain the size of that blob, or will it help?
Yes.
In that question?
Yes. So it will provide a significant advance in a couple of directions. So first, because we're replacing the front end facility AO system, it becomes AO 3000 instead of AO 188. That means we're getting an extreme AO correction even before we get to SCExAO. And then the SCExAO then just cleans up the rest of that. Coarsely, what that means is that the image quality is going to be so good that we might not have to do complex PSF subtraction even from the ground in the near infrared to be able to get a detection. In our highest quality data, we can see AB Aurigae B in the raw data in a few cubes obtained with SCExAO cares. That case will become the norm, I think, once the upgrades are completed. The other advantage is that in the optical, because now we're having a 2-stage extreme EO system, we will get diffraction limited imaging in the optical at a very high sterile ratio. That will allow us to be able to detect this object much more cleanly at H alpha than we could do before. So right now, what we have to do is we have to do some frame selection for data obtained in H alpha to be able to get a clean detection of the companion. And the image quality jumps around a lot because the sterile ratio you get at 0.6 microns is going to be a lot lower than you get in the near infrared. That will not be a significant problem anymore. So overall, we're able to just get a much cleaner detection of AB Aurigae B without nearly as much effort with post-processing, and thus a much cleaner interpretation.
So I guess that means the disk itself will hopefully be looking more robust from image to image.
Yes.
Because of the post-processing. So, okay.
Exactly.
Right. We do have a question from John Chambers. John, you want to take over?
Yeah, well, you may have partially answered what I was going to ask, which is one of the issues is knowing when you really are looking at real features compared to artifacts. And I know interpreting the ARMA images has got some of the same issues. So what are the prospects or the procedures for actually knowing when you really are looking at something real as opposed to an artifact of the processing?
That's a great question. So I think there are a couple of lines of evidence that you need to pursue. So if you expect this to be a protoplanet instead of a disk feature, it definitely should be detectable in thermal emission. It probably will not be detectable in polarized light. It should move, and its spectrum should be different from the spectrum of scatter starlight. And ideally, also, if it's a protoplanet that's actively accreting, it should be detectable in H alpha. So if you combine, that sort of gives you a sort of a checklist for things you need to go through to be able to convince yourself that the evidence favors a protoplanet versus a disk feature. So along those lines of evidence, I think the interpretation of AB Aurigae B as being a protoplanet is pretty strong. The interpretation of the calcium 15 BCD is weak for being a protoplanet. And there are a bunch of other systems that are sort of like in the middle. So for those of you familiar with the literature, there's an object in the Southern Hemisphere, HD 100546, that has at least 2 claimed protoplanets. That case is pretty messy. And so that's in the case where some diagnostics appear to point one way and some diagnostics appear to point the other way.
If I can just follow up on that, if you're interested specifically in the nature of disk features, what are the prospects for knowing whether what you're looking at is a real disk feature as opposed to an artifact? Yes.
So as a general rule, the advanced PSF subtraction techniques that are used to be able to get a detection in the first place tend to distort. Well, first they distort and reduce the flux of point sources. They do that in spades with disk features. And now with point sources, you can sort of forward model the effect of this distortion because you know what your prior is, because it's a point source, so you know what a point source is. So you just insert a synthetic point source of the image and you forward model it. Much tougher with the disk because disks are morphologically complex, they're extended, and it's sort of like tail chasing a bit because you have to be able to forward model the structure of something that you're trying to identify in the first place. So a partial way around this is with a new technique that my collaborator, Kellen Lawson, has developed, which is called polarimetry constrained differential imaging. Basically, we used the polarized light detections of the disk as your input for your forward model for your total intensity detection. And you can use sort of a least squares convergence to be able to convince yourself that the feature that you see in total intensity is actually real. It's not perfect. It relies on having good complementary data, but that's at least one way in which you can sort of make the challenge slightly easier. But really, the true answer is get a better AO system and just to the point where you don't have to use all this trickery to be able to get a detection in the first place. But that's easier said than done.
Thank you.
Okay, very good. We've got a question now from Scott Shepard. Scott, take it away.
Yeah, thanks for a great talk. My question is, we've been observing some of these disks for decades even, and we're getting better and better resolution. Do we expect to see the features to change over time? Are we seeing any change in disk structure? Would we expect to see any of that, or would we just expect the structure kind of be more or less the same?
It's a great question. So I think one of the challenges with that is, as you say, the quality of the images is evolving substantially. So it can be a little bit tough to compare an image taken in 1999 with STIS to one taken now. But as a general rule, I would expect you would start to see some variability in disk structure. For example, if you have an inner region of the disk that is puffed up and that is shadowing part of the outer disk, as that feature rotates, as that feature orbits, that will induce variable shadowing in the outer disk. So you might see a variable brightness levels for some regions, the outer disks in these particular systems. There's at least one system where we think we have evidence of this very clearly, but it's still in preparation. So as a general, I would expect so. Yeah. Now, in terms of like maybe spiral arms appearing or disappearing, that I'm less sure of. I would expect those features to be as those are often like locally produced or caused in part by things that are not happening right near the star. Those I would expect those to be a little bit more constant. It might be possible though to see a rotation of spiral arms in some of these systems though, and that may tell you a little bit about where planets that might be responsible for these arms could be located.
Yeah, I guess one of my question there is, if you had circular planets versus eccentric giant planets, the eccentric ones I assume would probably change the eccentricity of the disk. And if they're close in, you might see some kind of change in the disk. Is that a true thing? Could you tell, I guess, if a planet's eccentric versus not eccentric based on changes in the disk, I guess? That's
a really good question. I know if I were a theorist, I would have an answer to this. I don't have an answer off the top of my head, but I think I know who to ask for that. So.
Well, I'll take a shot at answering that.
Exactly.
I think the answer is yes. If there's an eccentric planet with mass, it's going to be affecting what's happening in the spiral arms, but it might take a while for it to be discerned in the arms, and just trying to disentangle. If all you saw was strange behavior in the arms, it might be very hard to uniquely point back to what was causing that, as opposed to the arms themselves, which have presumably some mass interacting with each other. So it gets really messy really fast. A lot of free parameters for theoreticians, but that makes theorists happy, because give them enough parameters, they can fit an apple with an orange if they need be. Okay, thanks, Scott. Any other questions from anyone? We don't have any questions on the chat window. So, but I will draw everyone's attention. At least I've got 6 or so of you who are going to be meeting with Thayne this afternoon. And there's a new Zoom meeting link that's shown up in the chat window, as well as in the most recent email from Alicia Alexander, showing you the link for the Zoom meetings this afternoon. So as long as people are aware of that, let's thank Thayne again for a wonderful talk, and we'll draw this part of the day's activities to a close. So thank you very much, Thayne.
Thank you.
Now, Thayne, what I suggest we do is